Hi everyone, this is 12.1 chi-square test for univariate data. All right, so let me tell you a little bit about chapter 12 as a whole. In chapter 12, we're going to talk about 3 different chi-square tests. Today we're going to talk about the chi-square test for goodness of fit, and then our next one will be a chi-square test for homogeneity, and the last one will be a chi-square test for independence. Now, these are all hypothesis tests. Now, the biggest difference, though, between the hypothesis tests we've done before and the ones we'll do in this chapter is now we're talking about categorical variables. Before, we've done hypothesis tests for means and for proportions, and these were all numerical. And now we're going to talk about how to do a hypothesis test when we have categorical data. All right, so let's jump right in. So right here, a test for whether the distribution of counts in one categorical variable matches the distribution predicted by a model is called a goodness of fit test. All right, so this is goodness of fit test. All right, now when we do our null and alternative hypothesis, these are no longer just mathematical symbols. These are going to be sentences. All right, so you'll do a sentence for both of them, and the null hypothesis is always going to be a sentence in context about the distribution matching what we expect or being uniform. And by that I mean being the same across. All right, so about the distribution either matching what we expect or being uniform. And so our alternative hypothesis is going to be the opposite. It'll be a sentence about the distribution not matching what we expect or not being uniform. All right. Now, let me give you a few examples of that so you understand what that means. So for example, let's say we're talking about the distribution of colors of Skittles. All right, and so we have all these different colors, and let's say we expect them to be uniform, that you would have the same number of red Skittles as you would do green Skittles, yellow, and my favorite, purple. All right, so let's say our null hypothesis is that the colors, all the colors of Skittles are uniformly distributed. That would be my null hypothesis, that we think that it's going to be the same number across the board. So the alternative would be that we believe that the color distribution of Skittles is not uniform, that they're not the same across the board. All right, so that would be kind of a uniform situation. A matching situation would be if we expect a certain percentage in each category. Like let's say we're talking about, M&Ms. All right, so same but colors of M&Ms, and we see from, the M&M company that we should expect 30% blue, 20% red, 10% yellow, and that's a distribution that we expect. So we would say something about the distribution of colors of M&Ms matches the distribution given by the M&M company. And then the alternative would be that it doesn't match. All right, so I'll show an example of that. Let's go to assumptions and conditions. We have 3 of them. And so the first one is going to be, as always, random sample. And our second one is going to be that all expected counts are greater than or equal to 5. All right, I'll explain that more when we get to our example. And then our last one is that data are in counts. And that last one is just to verify that we are doing categorical variables, right? So like colors is a categorical variable, and we're just counting how many are in each category. So that last condition is that the data are in counts. So you have an acronym right there for you. RAD. Okay, so those are 3 conditions, and again, I'll explain a little bit more when we get to our example. Okay, so next would be our statement, and our statement's going to be a little bit different than what we're used to, because instead of doing a normal model or a t-model, we actually have a chi-square model. All right, so here's a picture on the left of what that chi-square model looks like as degrees of freedom increases. So yes, chi-square model also has degrees of freedom. All right, and that should actually be a chi-square. So it looks kind of like a fancy capital X squared. All right, so a chi-square model is actually starts off right skew when it has low degrees of freedom, and as the degrees of freedom increases, it gets more and more symmetric, or more and more normal. And how we find degrees of freedom is that we have k minus 1 as our formula. So this is different than the t model, which was n minus 1, the sample size minus 1. This time, k is the number of categories. All right, the number of categories. So if we were to do our M&M example, let's see, M&Ms we have red, blue, green, orange, brown. I feel like I'm missing one, but let's pretend there's 5 colors of M&Ms. Then our degrees of freedom would be 4. All right. So number of categories minus 1. Okay. So we're going to be using a chi-square model with some degrees of freedom to do a chi-square goodness of fit test. And that will be our statement. Okay. Next comes our calculations, and our chi-square test statistic is this guy right here. And we have the observed counts minus the expected counts squared all over the expected counts for each category, and then we add them all up to get our test statistic chi-square. All right, and I'll show you guys how that's done, and also your calculator does that for you as well. All right. And getting into a little bit of the calculations also from that test statistic, we're also going to be finding a p-value. So the p-value, and I'm just going to use this chi-square in the graph as our example. Like, let's pretend we've had degrees of freedom of 15, and that is our chi-square model that we're focusing on. If our chi-square is here, our p-value, excuse me, our p-value would be this area to the right, and it's always going to be to the right. Because as the deviations from the expected gets larger, the chi-square gets larger. There's no way for it to kind of deviate to the left. It always kind of deviates to the right. So if the observed counts don't match the expected, that test statistic chi-square will be too large. It can't be too small. All right. Oh, and just so you know, we're only going to be doing hypothesis tests. There's no way to do a confidence interval for chi-square since it is categorical variable. You can't catch a categorical variable between two numbers. You just can't do it. All right. So let's go ahead to an example onto the back. All right, so this is a real life situation that I found myself in when I was teaching at Maranatha. And before, when I was teaching at Maranatha, we didn't have Power School. And so in order to randomly call on students to answer questions and volunteer, I used my TI-84 random number generator. So I had a roster, and I numbered every student on my roster, 1 through 30, whatever the class size was. And then I would have my TI pick a random number and find that name, and that would be the person I called on. So I did this pretty regularly. And then I was teaching honors algebra, and there was just this one student that would always get called on every single day without fail. And so because of that, at one point, he just said, "I think your calculator is not random. It's picking on him." So I happened to be teaching chi-square at the time, and so I'm like, all right, well, let's test that theory out. So what I did was I had him generate 100 random integers from 0 through 9 and count how many of each comes up. And these are the observations that he got. So he got, 10 zeros, 10 ones, 11 twos, etc. So these are the observed counts that he got from picking 100 random integers. All right. So to test to see if this is really a random number generator, let's start with our null hypothesis. So our null hypothesis would be that the TI actually is truly random and that there's no bias. So if that were the case, we would expect each number to have the same chance of getting picked, meaning that the outputs of the numbers would be uniformly distributed. All right, so I'm going to write a sentence about that. So the distribution of numbers outputted, is uniformly distributed. Sorry, 1L. All right, so the distribution of numbers is uniformly distributed. So we're in the case, this example specifically is about whether or not the numbers are uniformly distributed, which shows that it's a random calculator. Keep in mind there is another type of null hypothesis for this test, is whether or not it matches a given distribution. All right, so this is not one of those types. All right, so since that is my null hypothesis, my alternative is that the distribution of numbers outputted is not uniformly distributed. Okay, so that is my alternative hypothesis. Okay, so now let's go ahead and let's check these conditions. So first condition, random sample. So I let my student kind of pick a random time to check my calculator. It wasn't, set up in a certain way. So I'm going to assume random sample. All right, and then now we get to our second condition. All expected counts need to be greater than or equal to 5. All right, so if we go back up to the chart here, let's figure out what our expected counts should be. In this case, if the null hypothesis is true, how many zeros would we expect? if we picked 100 random numbers. So if the null is true, that the output is uniformly distributed and there are 10 different numbers, we would expect 10 zeros to come up out of that 100. And same with ones. I would expect 10 ones, 10 twos, 10 threes, 10 fours, etc. All right. And so these are our expected counts. Like these are the counts we would expect if the null hypothesis is true. All right, and since they are all 10, we actually do meet that condition that all expected counts are greater than or equal to 5. All right. And then our last one is that data are in counts. All right, so we're treating the numbers 0 through 9 as categorical, and we're kind of seeing how many of each category comes up, and we're counting those. All right, so on to step 3, our statement. So since we've met all those conditions, I will use a chi-square model with, now we look at how many categories there are. There are 10 of those categories. So we have 9 degrees of freedom to do a chi-square goodness fit test. And you can just label that GOF. All right. So that is our statement. Okay, let's go on to calculations. So calculations, I'm going to show you guys how to do this by hand, and also I'll explain to you how to do it on your calculator. All right, so the calculations, basically what we're trying to do is trying to see how far off are the observed counts from what we would expect. So I just labeled that resid, and that just is the difference between the observed and the expected. All right, so let's go ahead and find those differences. So we got 0, 0, 1, 3, 1, -3, 3, -1, -6, and 2. And we're going to square those so that those all become positives. We don't really care if it's above or below. We just want to know how far away it is. And so we're going to square all those. And then we're going to find the chi-square contribution for each of these categories. So if you look at the formula that we had in the front, it was observed minus expected square all over expected. So we already did the observed minus expected square. We just need to divide by expected. Our expected, luckily here, is 10 across the board. So if I do 0 divided by 10, I get 0. 0 divided by 10, I get 0. 1 divided by 10, I get 0.1. 0.9, 0.1, 0.9, 0.9, etc. 0.1, 3.6, and 0.4. All right. And what we do is we add all those numbers up, and that will be our chi-square statistic. So if we add those all up, we get a chi-square of 7. All right. So that is our test statistic, and now we just need to find our p-value. Okay, so to find our p-value, I'll do this on the side here. What I'm doing is I am taking that chi-square model with 9 degrees of freedom. My chi-square is 7, and I'm finding that area to the right to find my p-value. So in your calculator, we're going to go second vars, or second distribution is what it says in blue, and the button says vars. And this is where we normally put, or we get normal, CDF. This is where we also found our binom and geomet. If you scroll to number 8, you see a chi-square CDF. And in that chi-square CDF, we're going to put 7 as our lower, a big, big number for our upper. Degrees of freedom would be 9. And then we get our p-value of 0.6371. All right, and that is how you find your p-value. Okay, so that's how you would do it by hand. All right, now to kind of shortcut this, what you would need to do is, since you have your calculators out, so restart, pretend we just finished the statement. We're about to go into calculations. We don't know chi-square, we don't know p-value. Go ahead and hit Stat and go Edit, and you see your L1 and your L2. What I want you to do is put your observed counts into L1 and then put your expected counts into L2. So observe L1, we're going to put 10, 10, 11, 13, 11, 7, 13, 9, 4, and 12. And then move over to L2 and just put 10, 10, 10, 10, 10, all the way down 10 times. All right, so your L1, your L2 should have the same number of items in them. Okay, next go to Stat, move over to Tests, scroll to chi-square GOF test. My calculator, that's letter D. And the observed should be L1 already. The expected should be L2. Degrees of freedom, change that to 9, and then press calculate. All right, and that is your chi-square of 7 and p-value of 0.6371. All right, so we're ready to move on to our conclusion. So our conclusion now is that's a pretty high p-value. So since the p-value is so high, I fail to reject the null hypothesis. There is not enough evidence to suggest that, and this is kind of the best part of chi-square test, your alternative hypothesis is already in sentence form, so you literally can just copy what you wrote in your alternative to suggest that the distribution of numbers outputted is not uniformly distributed. And if you want, you can even put the kind of final end to this, which suggests or implying the calculator is fair. And I wasn't picking on that student. Okay, so that is a chi-square test. All right, go ahead and practice with your homework problems and email me if you have any questions.